In section 6.2, we are going to be looking at the definition of working energy in a mathematical form. And we said energy was defined as work. Now, how do we define work? Well, work is given by the force times the distance. And actually, this is a dot product, meaning that we take if we have a force in this direction, and we push it in this direction, say this is a distance r, or dr, then both of these, the direction that we're pushing it and the force, are both vectors. And we define the work to be the force dotted with dr, as a dot product, so it is the F times the cosine of theta times delta r. Now that basically says if this is the angle theta, this part here is F cosine theta. Now what that means is it's the force that's in the direction of motion times the distance that you're pushing. Force in the direction of motion times the distance you go. So if I'm pushing on that lawnmower, it's only the force that's in the forward direction that's going to do your work. The other force is just trying to push the lawnmower into the ground. I'll draw the picture of that for you. There's the lawnmower. You're applying your force down in this direction. Then, of course, there are two components of that force: the part that mows the lawn, moving you forward, and the part that just pushes you down into the ground, which doesn't do any work that's useful. So we need to think about what the units are for this. Of course, cosine theta has no units, but F has the units of a Newton, and the change in distance, or the distance I go, is a meter. So work or energy is given in Newton meters. But we give a name to this. We call this a joule of work, for the man whose name was Joule, who first discovered the conservation of energy. So a joule, J-O-U-L-E, or equivalently joule, is equal to a Newton meter. A Newton of force pushing for 1 meter of distance gives us 1 joule. And therefore, this is a very important fundamental unit of measuring all of our energy. It's in the form of joules. You can probably say at this point, well, I've never heard of a joule. I've heard of barrels of oil. I've heard of all kinds of other kilowatt hours, all kinds of energy units, but I've never heard of a joule. That may be, but you have heard of power defined in terms of a joule per second, which is a watt. So we'll find in a moment that 1 watt is 1 joule a second, or effectively a 1 watt going that much power applied to something for 1 second is the same as 1 joule. Okay, now that we've gotten this established, let's imagine that we push on our lawnmower. We're going to push on this lawnmower at an angle theta, like 20 degrees. We're going to push with a force of 30 newtons. We're going to go a distance of 100 meters. Then what would our work be? How much work or how much energy do we expend? Well, our work is going to be our force, which is going to be 30 newtons, times the cosine of the angle, cosine of 30. I'll put 20 there. Let's put 30. Then it'll be easy to calculate. Cosine of 30 times the distance I go, which is 100 meters. So the work is going to be equal to, for mowing this lawn, cosine of 30 is 1/2, so that gives us 15, and we have 15 times 100, so it's 1,500 joules of work. 1,500 joules. And remember again, it's a scalar. It doesn't point one direction or another any more than heat or mass or temperature point one direction or another. Now, to be a little bit more precise with calculus, if the force varies over a distance, then we take, as we move along a curve, we take the infinitesimal force, take the force times the infinitesimal motion, I should say, dr, and take the dot product of those, F dot dr, and that gives us our infinitesimal work. Consequently, it follows that our work is the integral from point 1 to point 2 of F dot dr. And so if your work is constantly changing and changing in force is changing in direction and magnitude, then if we want to compute the work, we have to integrate that by dotting it with the distance that we go in the direction of the force, and then by using the cosine of the angle, and integrate that from the first point to the second to see how much work we do in going from point A to point B. The unit of work, as I've mentioned, is 1 joule, which is 1 Newton per meter. And if the force is called what is called conservative, then this integral is path independent. And it's 0 for any closed curve, meaning that if I go around a closed curve, the work around a closed curve would be what is called an integral around a closed curve, F dot dr, and that's always equal to 0 if and only if F is conservative. What's a conservative force? It basically is a force that doesn't lose any of the energy to heat, therefore the second law of thermodynamics. For example, if a perfectly frictionless object is pushed up a hill and allowed to roll back down in a path like this, then in fact as it goes up and goes down around this path, it'll keep going. Maybe there's a spring down here to push it back up. When it comes back down, hits the spring would throw it back up. It changes its kinetic into potential, and you just have a cycle there where it would go on forever if there was no heat. Such an example is where if we go around this curve and take F dot dr everywhere and integrate it, we get 0. What does that mean? It means we get the same energy back in one direction as we exert in the other direction. It just changes form from one thing to another. And so the total integral around the path is said to be 0, or it's path independent. Such forces are called conservative. And basically the simple way to think of a conservative force is you lose no energy to heat. Well, let's next look at the concept of kinetic energy. Kinetic energy is energy of motion, and the equation for kinetic energy is 1/2 the mass times the velocity squared. It is energy of motion, therefore it depends upon the velocity, and you'll notice it depends upon the square of the velocity. If your car is going at twice the speed, it is 4 times the energy. And regrettably, when you hit that brick wall or concrete abutment, you're going to have 4 times the damage that you would have if you were only going half the speed. Well, a typical question that I like to use here is for a football player. Let's get out the football player and say, what does a football player weigh? Well, let's take him at 220 pounds. Well, 220 pounds is exactly 100 kilograms. We're going to use that. Now, how fast is this football player going to go? Well, just to make the calculation simple, what we're going to do is we're going to take this football player as though he's a real track star. The record has been broken for 100 meters in 10 seconds. So we can look at 100 meters divided by 10 seconds, or 10 meters per second, as about the fastest that anyone has run in the Olympics or right at the world record. So we're going to let our football player run that fast. We're going to say, okay, what kind of energy does he have? He's going to have 1/2 his mass, 100 kilograms, times the velocity squared. That's going to be 10 squared. So if we work this out, we get 50, 1/2 of 100, and we get 2 more zeros here, or 5,000 joules, or 5 kilojoules. So 5,000 joules is the energy that this 220-pound or 100-kilogram football player would have. Incidentally, if you look at a woman who weighs 110 pounds, which is only 50 kilograms, you can see that her energy, even running at the same speed, would be half as much. So that's why so many things in athletics are dependent upon weight. If you double the weight, you double the energy and the force and everything else. So this gives us an idea of how to calculate the kinetic energy. You can also calculate the kinetic energy of an automobile. It's a simple, easy problem to work. That gives us kinetic energy. Let's go now to potential energy due to gravitation. I'll move the paper up here a little bit. We're still on section 6.2, and we're going to take up now gravitational potential energy. Well, if we have a mass on the floor, this is a table, and we take that mass and you put it up on the table, it turns out that gravity is a conservative force. If we don't slide it along some surface, in fact, we can get all of that energy back. So to do this, to put the mass up on the table, we know that the force of the mass downward is mg. So we have to exert an upward force of mg to balance that exactly and move the mass up onto the table. So we know that our work or energy that we perform is going to be equal to force times the distance. And our force is going to be mg. That's how hard we have to push upward. And we're going to raise it a distance, delta x, or let's call it the height h. Let's say that we have a table of height h. And you'll notice that the force is directly upward, and our direction that we move it is directly upward, so we don't have a cosine of an angle. So generally speaking, we can say that the potential energy due to gravity is m times g times h. Well, this may astound you, but it turns out that if you want to store energy in large amounts, the best we know how to do with our technology, as crude as it sounds, is to take water and run it uphill. When the water is up in a lake, we can let the water flow backwards down to a river, as we do in reservoirs that are used to store energy for nuclear power plants. And as the water runs back down through the turbine, we get that energy back again. You might ask, how much do we lose in that whole process? Taking a river, pumping it up to a higher lake, and then letting the water run back down, it turns out you can do that at about 85% efficiency, which is really quite remarkable. Okay, let's just imagine we're going to do something very simple here. One thing that we might do is, this is a truck. Doesn't look quite like a truck, but imagine that we have a truck here, and we want to put bricks on that truck. And let's say that we have these particular rocks or bricks that we have are going to weigh 10 kilograms each. That's about 10 kilograms is going to be 22 pounds. And we're going to put these 22-pound stones up here, and let's imagine that this is about countertop level, which is 36 inches, or let's say 1 meter, slightly over 1 meter. If we do that, and we have, let's say, 500 of these bricks, and we want to put them up here, then how much work are we going to do? Well, our work is going to be equal to our force times our distance. There's our force, there's our distance. And how do we work it out? Well, we have 10 kilograms for our mass. G is 10. Our height is 1. And we're going to do this 500 times, because we have 500 of these stones to put in the back of this truck. Well, that would give us 500 times 10 times 10, or 50000, or 50,000 joules of energy. And that's how much work that we would have to do in order to load that truck. Equivalently, you could look at water that was being pushed up a hill for a nuclear power plant. The next one I want to work has to do with elastic energy, because often we compress something like a spring or pull a spring out, and the potential energy that's stored in such a spring, the potential energy is given by 1/2 kx squared, where x is the distance from equilibrium. In other words, if I take a spring with a mass on it, and this is the equilibrium point, and I stretch that string out to a distance of 8 meters, then in fact, if it has a spring constant with k is equal to 3, then my potential energy I've stored by stretching or compressing, either way, that system is going to be 1/2 spring constant times 8 times 8 is going to be 64. You'll notice that that squares. Half of that's going to be 32. So 32 times 3 would be 96. So we have 96, joules of energy. And that tells us how much energy we have as by virtue of storing that in the spring. Now we're going to work some problems in just a few minutes having to do with how we conserve energy and how we convert it from one form to another. We could let a pendulum swing. So as the pendulum swings, we're converting kinetic energy at the bottom to potential energy right up at the top, just like swinging on a rope. Or we could compress a spring and then let it fly apart and send the mass going with a high kinetic energy. Or we could let kinetic energy push something up a hill and store it with potential energy. We'll cover that in the next section. In the meantime, what I want to do is, for the more advanced viewer, I want to do a quick calculation on where we get our kinetic energy and where we get our potential energy, like our spring and this energy here. So this derivation is a little bit more sophisticated. Again, we're still in section 6.2 as I work along here. Now, what is work? I want to look at kinetic energy. I want to derive it. Our infinitesimal work is our force times our infinitesimal distance. Oops, dx. And it's the dot product of the two. Let's assume for the moment that they're in the same direction. In other words, the force is pushing in the direction of motion, so we can forget the vector signs and write it as f dx. Now we know what force is. It's mass times acceleration. So this is mass times acceleration. I'm going to write that as dv dt times dx, because we know acceleration is change in velocity over change in time. Now I'm going to divide dx by dt, and I end up with the change in work is m dv dx dt. But dx dt is velocity itself. So this is velocity. So this is equal to mv dv. Well, this is kind of neat now, because I've ended up with a formula dw is equal to mv dv, and I can integrate both sides. When I integrate here, the mass is constant, so it moves to the outside. The work then, or the change in work, is going to be equal to m times the integral of v dv, and as you know, that integral is 1/2 the velocity squared, evaluated between the upper and the lower limit. We're going to evaluate it between 0 and v. We want to be able to compare it to no motion at all. And so that would give us 1/2 mv squared, and there's our kinetic energy. So it's a pretty simple derivation, and you need to have seen that if you're aware of calculus. The next one is the potential energy, and of course there we have an infinitesimal force times, or let's say a force times an infinitesimal distance. That'll give us our work. It's infinitesimal, and so we integrate both sides. The work here is constant. It's going to be mass times acceleration. So the change in work, or the change in energy, is going to be mass times acceleration times distance. wait a minute, let's see. I'm going to do that force as I go up. I don't need mass times acceleration. The force is m times g, where g is constant. And therefore, I can just integrate the distance that I go up. And the distance that I go up from zero, from the ground level up to a height h, is simply going to be mgh. So we can see that when I raise a mass, its gravitational potential energy or work that is required is mgh, whether I'm moving water uphill or moving bricks. Finally, I want to look at the spring. You recall that the spring force is minus k times x. Well, that's the force that the spring is pushing with, but we must push in the opposite direction to overcome the spring. And so when we take the spring force and say, what is the work that we do? The work that we do, infinitesimal work, is going to be force times infinitesimal distance, which will be k times x dx. Again, we want to integrate on both sides. You'll notice here the f changes. It's not like here, where it was just a constant. That's because the force changes with the more you pull that spring out. So this is the work from 0 up to a certain amount of work, where there's, we could say change in work, and that's going to be equal to k times integral of x dx, which is 1/2 k times x squared, evaluate between x and 0. In other words, we want to use our reference point where there's no elastic stretching of the spring, and this gives us our work for our spring. Therefore, the potential energy of a spring is encapsulated because of the square there. So we end up with a square both with the spring energy and with the kinetic energy. Right here, kinetic energy is potential energy of gravity, potential energy of a spring.